Hello guys and welcome to this examination past question review. We are looking at the modeling of electrical systems and the question goes thus. For the electrical system shown below, derive the differential equation relating voltage V naught of t and Vi of t. So this is the electrical system shown below. There's a B part to the question. It says if the inductor is neglected, what will be the effect on the order of the system? So let's quickly go through this question and see what it is. Okay, so solution. All right, so to determine the differential equation governing this system, all of you are all engineering students, so you should have had experience of what we call Kirchhoff's voltage law. So Kirchhoff's voltage law is your ticket to resolving electrical circuits. Okay, Kirchhoff's voltage law, unlike in mass spring systems where we had to apply D'Alembert's principle, okay, and choose a reference direction. So Kirchhoff's voltage law, and we have to pay attention to the direction of the current. If there is no direction of current given to you, you need to define a direction of the current, define a current and define the direction of the current, and make sure you abide by that direction, following all the rules, and you might still be able to get the correct answer. Hopefully you will. So we are going to apply Kirchhoff's voltage law to this particular circuit. If you apply Kirchhoff's voltage law to this particular circuit, so applying KVL, okay, you're going to have VI of t is equal to, so VI of t will be the sum of the voltage across the resistance plus the voltage across the inductance plus the voltage across the capacitance. That's our first equation. So we have VR plus VL plus VC. Is that okay? So this is equation 0, for instance. So if I express this one in terms of the current, I have my VI of t is going to be VR is the same thing as R times I of t, okay. Then VL is the same thing as L, voltage across an inductor is the product of the inductance and the derivative of the current, okay. Then plus voltage across the capacitor is going to be the same thing as 1 over C integral of the current dt. So where C is the capacitance. Okay, so this is equation 1. Okay, so you also have to take note of something. Now, the voltage across the capacitor is still equivalent because they are taken from the same terminals. VC is going to be equal to what? V naught of t. That okay? VC is still the same thing as V naught of t. Now, they're asking us to find the differential equation that relates, okay, that relates Vi of t and V naught of t. So this is one way of expressing the differential equation. I'll still get back to something, but I just wanted to express it like this for now. But I also wanted to express that Vc is still the same thing as V naught, okay, and both of them are 1 over C integral of I dt. So the output voltage is still the same thing as the voltage across the capacitance, and it's still the same thing as the voltage on the capacitor. So this voltage has been distributed into here, here, and here. Is that okay? Where this one, VC, is still the same thing as my output voltage. So that's what I mean by these equations. Is that okay? So to make this equation much more interesting, because we don't want to leave it in integral form, okay, there are two things we can do. So two ways. So two ways is we have in terms of current. So in terms of current, if we differentiate equation 1, okay, with respect to t, differentiating through with respect to t, we'll have the Vi of t by dt, okay. Then if you differentiate this one, you have R, okay, di dt, then plus differentiating this term, you have L second derivative plus. So if you differentiate an integral, you're just going to get the argument of the integral, making it I divided by C. Okay, so this is actually what equation 3. Is that okay? So if you also, let's say you call this one, you called this equation over here equation 2. If you differentiate equation 2 with respect to t, so differentiating equation 2, differentiating 2 with respect to t, okay, differentiating 2 with respect to t, we'll have the vc by dt is still the same thing as the v naught by dt, which is still the same thing as I over c. Are we together? So differentiating equation 2 with respect to t, we've gotten this particular case. So I'll put it as equation 4. So it means that I can actually replace what? I can replace this I over c that is occurring in 3 with this particular equation, or this particular expression here, dv naught over dt. Is that okay? Because we want to find the relationship between this and this, the output. So I can say, we can put 4 in 3, and this will yield what? A second order system or differential equation. The v input of t by dt is equal to r di dt plus l d 2I by dt squared. Then plus, instead of I over c, I can have the v naught over dt. Is that okay? So let me write it well. So we could have it like this. Is that okay? So this is our second order system. Okay, second order system, I can call it equation 5. So this equation finds the relationship between my vi of t and v naught of t. So in terms of charge, you need to know that q is equal to it, or q bar, or I is dq dt. All right, so this is the expression that we normally grow up with in physics. Charge is equal to current times time, but more practically in differential form, current is the rate of change of charge. Okay, rate of change of charge, I is equal to dq all over dt. So you need to consider equation. Which of the equations are we considering? Consider very, okay, consider this particular one. Okay, consider this one over here. I'm going to copy it and I'm going to paste it. So this was equation 1. So consider equation 1. It was given to us like this. All right, so before I proceed, I want to say you can actually stop here in equation 5 because you've already expressed it in terms of current. So we want to look at another case. Someone else might solve his own using charge. So if you're using charge, you consider equation 1. So if you're using charge, you consider equation 1, and you have to consider that I is what? The q dt. Now if you differentiate both sides, the I dt is going to be the second derivative. Is that okay? The 2q by dt squared. And you also have to consider finally that to get q, you can take the integral of I with respect to t. Okay, from this formula, the q is equal to I dt, therefore q is integral of I dt. So consider these 3 things holding for q. So if you replace this particular equation with the charge equivalent, vi of t is going to be what? R. Okay, so instead of I of t, we'll have dq dt, because current is rate of change of charge, plus L. Instead of current and the first derivative of current, we have the second derivative of charge. Okay, then plus, instead of integral of I of t, we'll have 1 over c, then the integral of I of t is equal to q. So this is equation 6. So it's still the same thing. Okay, it's still the same thing that we had, making reference from this particular equation. Okay, making reference from this particular equation 2. So I'm going to copy equation 2. Okay, so that we'll just wrap it up. So from equation 2, sorry, something is happening. From 2, okay, v naught is equal to 1 all over c. So if you replace this one with q, v naught is still the same thing as 1 all over c dot q. So this is equation 6b. So if you put equation 6b in this equation 6, what you will be left with is your vi of t in terms of charge will be r d2 r dq dt and plus l d2q over dt squared. Then you now have plus this whole term is now going to be replaced by this whole term, which is my v naught of t. Is that okay? So this is my v naught of t. So this is another equation that relates, okay, the input voltage to the output voltage. So the second part of the question asks us what happens to the order of the system if we neglect the inductor. So if we neglect the inductor, we are simply replacing L with 0, assuming it never exists. So replacing L with 0, take note that this is a second order, okay, because you have second derivative present. So if you replace L with 0, you have your Vi of t is equal to R dq dt, okay, plus you will have what? V naught of t. So this becomes first order in terms of charge. Or those of you that stuck to the current version of the equation, remember this is the current equivalent of the equation. So if you stick with the current equivalent of the equation and if you replace, let me just copy this one and break it down there. If you replace L with 0 as if it never exists, if you replace L with 0, or let's take it up there. Control Z. Okay. Or from equation 5, putting L equal to 0. Since it's also in second order form, the highest derivative d2i over dt squared, we'll have v dt is going to be r di dt. L equal to 0 makes this term cancel, plus the v naught of t all over dt. So this becomes first order, okay, in terms of I, okay, of t. So anyhow you express the answer, you should just be very flexible with the calculations and understand what is actually happening. So this brings us to the end of analysis and modeling of systems for now. I hope you might be able to practice some more examples. What if a system was actually represented like this? Okay, and instead of a capacitor, you have a resistor here. So let's say you have R1, L1, and you have something like R of R2. Huh? So let's say you have a V1 and you have a V2 at this end. Okay, so I want you to be able to prove that Okay, prove that V2 of S divided by V1 of S is the same thing as R2 divided by R1 plus SL in a half plus R2. So carry out this proof, and if you get your answer correctly, hit me up in the comment section and show me how you were able to solve it. But just practice something like this just to make sure that you understand the process. Is that okay? So thank you very much for watching, and all the best in your exams. Yeah, bye, stay blessed, subscribe.